Alrighty, in this video we're going to start section 2.2 and we're going to start to cover functions. And what we're going to learn in this section over the next 2 days are determine whether relations between two variables are functions or not. We're going to learn function notation and use it to evaluate functions. We will find the domain of functions, and we'll use functions to model and solve real-life type problems. And we will evaluate difference quotients. Alrighty, so let the fun begin. Introduction to functions. Many everyday phenomena involve two quantities that are related to each other by some rule of correspondence. The mathematical term for such a rule of correspondence is a relation. In math, relations are often represented by mathematical equations and formulas. For instance, the simple interest I earned on $1,000 for 1 year is related by the annual interest rate, or related to the annual interest rate R by the formula I equals 1,000 times R. The interest you will earn is equal to the amount you put in the bank, $1,000, times the rate. The formula I equals 1000 R represents a special kind of relation that matches each item from one set with exactly one item from a different set. Such a relation is called a function. So in the box is our definition of a function. A function f from set A to set B is a relation that assigns to each element x in set A exactly one element y in set B. The set A is the domain, or the set of inputs, of the function f, and the set B contains the range, or the set of outputs of that function. And graphically sometimes these make a little more sense. So here on the left is a blue box, that's set A, that is the time of day, PM. And in the other box over here, this sort of tan box I guess, is our temperature in degrees. If we notice in set A, the domain, we have 6 numbers. 1, 2, 3, 4, 5, 6. Each and every one of those numbers is matched up with a number over here in set B, the range. So we see that 1 is mapped onto the number 9. Number 2 is mapped onto the number 13. Number 4 is mapped to 15, and so is 3. 3 is also mapped to the same number 15. 5 is paired up with 12, and 6 is paired up with 10. So every member of the domain is matched up with only one member of the range, and this is going to classify or qualify as a function. So this function can be represented by the following ordered pairs, in which the first coordinate, the x value, is the input, and the second coordinate, the y value, is the output. So here we had the 1 was paired up with 9, that's 1, 9 degrees. 2 was paired up with the 13, 2, 13 degrees, and so on and so forth. Now notice up here, a real important thing to see is 4 got mapped to the 15, and so did the 3. That is perfectly legal. 2 different inputs can be mapped to the same output. But let's say if we had this occurring, this 4 is mapped down here to the 15. If we had another arrow from the 4 to a different number, that would be a disqualifier. It would still be a relation. Relations are just, sets of ordered pairs of things. But each member of the domain in a function is matched to only one member of the range. That is a critical part of being a function. So if this 4 is, paired up with 2 different numbers in the range, it fails the test. It would not be a function. So the characteristics of a function from set A to set B. Each element in A must be matched with an element of B. Notice again back to this picture. Oops. Get down there. There is no, let's say over here we had an open circle with a 7 in it, and that 7 was not paired up with a number in the range. That would also be a disqualifier and not a function. Each element in the domain must be matched with an element in the range. Some elements in the range B may not be matched with an element from A. Over here, we got these numbers. These numbers do not correspond to any number over here in the domain, and that's fine. Every member of the domain is used, but not every member of the range has to be used, or every number in this set that contains the range. So 2 or more elements in A may be matched with the same element in B, and again that was right here. 4 got mapped to 15, and so did the 3. That's perfectly fine. An element in A, the domain, cannot be matched to 2 different elements in B. So again, that would be, having 4 mapped to the 15, and the 4 may be also mapped here to the 1. You can't have one member of the domain paired up with 2 different members in the range. And we have here functions are commonly represented in 4 ways. Verbally, by sentences that describe how the input variable is related to the output. Numerically, by a table or a list of ordered pairs that matches inputs with output values. Graphically, by points on the graph in the coordinate plane in which the input values are represented by the horizontal axis and the output values are represented by the vertical axis. And algebraically, by an equation in 2 variables. Anytime you look at anything in math, you should be able to analyze it in 4 different ways. Verbally, numerically, graphically, or algebraically, or analytically, I guess you could call that. The poster I have in my classroom, you see VANG, V-A-N-G. And that's just an acronym I use to remember those. Vertically, analytically, numerically, and graphically. If you can understand a math concept from all 4 of those sides, you really understand what's going on. So let's see here in example 1. We're going to test whether a relation represents y as a function of x. So let's see here in part A. I guess we got to know a little bit from our civics classes here. It says the input value x is the number of representatives from a state, and the output value y is the number of senators. So we have to think, how many representatives does each state have? Well, that kind of varies. Different size states, different population. You might have 1 rep, or 2 reps, or 3 reps, or 4 reps. And the output value is the number of senators. Well, how many senators are from each state? Each state has 2 senators. So if we think about this graphically, 1 is paired up with 2, and 2 is paired up with 2, and 3 is paired up with 2, and 4 is paired up with 2. Is that a function or not? Well, each member of the domain is paired up with 1 unique member of the range. So yeah, part A, yes, it's a function. Here in part B, we have a table, inputs and outputs. An easy way to check this is just scan all your inputs. Look for repeaters. Here I see a repeater right away. We have a 2 and another 2. Now, if these are paired up with the same output value, that's fine. It's just, a double. But here, this 2 is paired up with 11. This 2 is paired up with 10. Right there, that is an automatic disqualifier, not a function. And let's see, here our last one is C. This is graphically. We see we only have a few points graphed. We could, fill in the dots and we could see that that is a parabola. How do we check if a graph is a function or not? Remember the good old vertical line test. I'm going to come up here with a vertical line. Remember, if we can slide a vertical line across the graph and only hit at 1 point at a time, it passes the function test. So we're going along here, we hit that first dot, and that's the only dot we hit. So right there, we're still a function. Keep going over, we hit that dot, and that's the only one we hit, so we keep going. We're only hitting one of those graphed points at a time. So the vertical line tells us here for part C, yes, that's a function. And this is a good area, I guess, to explain, why this table didn't work. Let's say I have my XY axes. And here's 1, and here's 2, and here's 3. If I graph these points, 3 gets mapped over to 8. So let's call this 8. That would be the point 3, 8. Here we have 2, 10. So 2, maybe 10 would be about right here. Here's 2, 10. And then the next point is 2, 11. So it's the same x value, but now I'm up here at a different y value at 11. So I have these 2 points right over top of each other. Would that pass the vertical line test? No. I would hit both of those points at the same time, and that would fail the vertical line test. Example 2. Testing for functions represented algebraically. So which of these functions represents y as a function of x? So what we want to do is solve them for y. This first one, letter A. My y is right here. I want to get it alone, so I'm going to subtract x squared. Y equals negative x squared plus 1. And before we even discuss this one, let's see what happens over here in B. We're also going to solve this for y. So we're going to add x to both sides. Y squared equals x plus 1. And now, of course, we know by this point in the year, to get rid of the square, we're going to square root both sides. And when we do so, we have a positive and a negative root, plus the square root of x plus 1, and the negative same square root of x plus 1. So here, when we plug in some number for x, when we plug in different x values, we are going to get y values. So here, yes, this would be a function. But let's think about this other one on the flip side here. Let's say I plug in x equals 3. If I plug x is 3 into this top piece, I get the square root of 3 plus 1. The positive square root of 3 plus 1, that is the positive square root of 4, which is 2. If I plug that same x value 3 into this bottom part, negative the square root of 3 plus 1, that's the negative square root of 4, or negative 2. I put the same input in. I put a 3 into each of these pieces of this function, and I got different outputs. So that's an automatic disqualifier. B is not a function. You know, again, that would sort of, if we graphed those points, that would be a failure of the vertical line test. A big part of functions is the notation that goes with it. When an equation is used to represent a function, it's convenient to name the function so that it can be referenced easily. For example, you know that the equation y equals 1 minus x squared describes y as a function of x. Suppose you give this function the name f. Then you can use the following function notation. Instead of having y equals 1 minus x squared, we would have f of x is equal to 1 minus x squared. You know, whatever x value we put into the function here, that would be our input, f of a number, and then we would get the output. So, x is the input, the output is f of x. Whatever that function does to x is our output. And here would be our equation, f of x equals 1 minus x squared. The symbol f of x is read as the value of f at x, or simply f of x. The symbol f of x corresponds to the y value for a given x coordinate. So you can write y is equal to f of x. They're the same thing. They're equivalent. Keep in mind that f is the name of the function, where f of x is the value of the function at that x coordinate. For instance, the function given by f of x equals 3 minus 2x has function values denoted by f of negative 1, f of 0, f of 2, and so on. To find these values, we substitute the specified input value into the given equation. So for the x value negative 1, f of negative 1, that's our input. We're going to go through this function and just replace the x here with that input value negative 1. So 3 minus 2x becomes 3 minus 2 times negative 1. Or 3 plus 2, which is an output value of 5. For x is 0. F of 0, we're going to take the same function and replace the x with the number 0. 3 minus 2 times x becomes 3 minus 2 times 0, or 3 minus 0, which is 3. F of 2, we replace the x in the function with a 2. 3 minus 2 times 2, or 3 minus 4 is negative 1. And again, here, let's tie this up. You know, f of negative 1. F of negative 1 equals 5. This is the value of the function at negative 1, and that value is 5. For the second one, f of 0 was equal to 3. The input to the function was a 0, and the output, or the value of the function at 0, f of 0, is 3. Although f is often used as a convenient function name and x is often used as the independent variable, you can use other letters. For instance, here's f of x. f of x is x squared minus 4x plus 7. Oh, we can still call the function f, but now let's call the independent variable t, f of t. So any place we saw an x, we're just going to replace it with a t. Instead of x squared minus 4x plus 7, now it's t squared minus 4t plus 7. And in the last one, let's change the name of the function. Instead of function f, now it's function g, and the independent variable is letter s. So g of s is now s squared minus 4s plus 7. And they all define the same function. In fact, the role of the independent variable is often that of a placeholder. Consequently, we could describe the function without, those independent variables at all. We could just say f of something is equal to that something squared minus 4 times that same something plus 7. Example 3, we're just going to evaluate a given function for different values. So our function is g of x. I'm just going to rewrite it down here to reference it easier. G of x is negative x squared plus 4x plus 1. First, part A, we're going to find g of 2. G of 2. So we're just going to replace any x we see with the number 2. Now careful, this negative is not part of this. It's not negative 2 quantity squared, it's negative 2 squared. And then we're going to have plus 4 times 2, replace that x with a 2, and then add 1. So let's see, here we get negative 2 squared is 4, plus 2 times 4 is 8, plus 1, so that turns into 5. So g of 2 is equal to 5. Part B, let me clear this out here. Part B, they just want us to find g of t. So any place in the original function where we see an x, we're just going to replace it with a different variable t. Minus t squared plus 4t plus 1. And we're done. Oops. Now the last one, this is sort of a little bit of a lead-in to calculus. We're going to have g of not just x, but x plus 2. So now be careful, we're going to replace any x we see with a quantity in parentheses, x plus 2. So minus, here's our x, we're going to replace that with x plus 2, and that's squared. Plus 4 times x, but we replace that x with x plus 2. And then we have our plus 1 at the end. And there we go. See here, example 4. Now, this might be the first time you've seen one of these. I don't know how much you got to it, maybe in Algebra 2. A piecewise defined function. It's sort of a function broke up into two pieces. And here's the real critical part. Here's our input values, our members of the domain. Here we see the function is broken into two pieces. We have this top piece, x squared plus 1, the bottom piece, x minus 1. Which piece of the function we use depends on what x value we're trying to put into the function. So if we're picking an x value that's less than 0, we take that x value and plug it into the top piece of the piecewise function. On the other hand, for the number 0 itself and all numbers greater than 0, we're going to take those x values and plug them into the bottom piece of the function, x minus 1. So here is our f of x equals these two pieces. First, we're going to evaluate at x is negative 1. F of negative 1. So first, we got to figure out what piece we put the negative 1 in. So negative 1, that's definitely less than 0. So we're going to plug that into this upper piece of the function, x squared plus 1. Something squared plus 1, and now that something we're plugging in there is negative 1. So we get negative 1 quantity squared, negative 1 times negative 1 is 1, plus this other one is equal to 2. Next, we're doing 0, f of 0. So what piece of the piecewise function do we plug it into? Let's see here. Well, if we're less than 0, we use the top piece. But we're not less than 0, we're exactly equal to 0. So we're going to have to use the bottom piece. For numbers greater than or equal to 0, we plug that value into the bottom function, x minus 1. Or something minus 1, and now that something is 0. 0 minus 1 is negative 1. So f of 0 is negative 1. And our last number to evaluate is positive 1, f of positive 1. So for numbers less than 0, we use the top piece. Now we're greater than 0, we're at 1, so x greater than 0. 1 is greater than 0, we plug that 1 in to the bottom piece of the function. X minus 1 becomes 1 minus 1, or 0. If I remember correctly, that is the last example for this section. Now for some practice for you. Team huddle. Number 12, determine if it is, whether the relation represents y as a function of x. Number 16, which sets of ordered pairs represent a function from a to b? This used to be a great question on the old PSSA test. I imagine you might see something like this on the SAT. That's another good one. 22, determine if an equation represents y as a function of x. And then here we have some evaluate. You know, the first one is just evaluate in the g function. 50 is a piecewise defined. So pause the video, try the huddle problems, and then fire it back up and see if your answers were right. And when we look at the first one, we have our inputs and outputs in a table. Remember the ordered pairs. You know, all your x values should be different. That's a quick way to scan to see if this is a relation or if it qualifies as a function. Well, of course it's a relation. It's sets of ordered pairs. It's things matched up. But is it an actual function? So scan your input column, or this row here. I see a repeater right off the bat, 0 and 0. They are paired up with different output values. Automatic disqualifier, not a function. Number 16. Which sets of ordered pairs represent a function? And here's a critical part. From A to B. So A is a set of lowercase letters, A, B, C. B is a set of numbers, 0, 1, 2, 3. So let's look here at letter A. I'm looking at my inputs, A, C, C, B. I notice a repeater. That C and that C go to different output values. Therefore, number A, or letter A, is not a function. It's no fun to not be a function. Let's look at letter B. My inputs, A, B, C, they're all different, so I can stop right there. That is definitely a function. Now let's look at letter C. The inputs, 1, 0, 2, 3. They're all different. So you're going to think right off the bat, aha, that is a function. Yes, it's a function. But here's a critical distinction. Function from A on to B. So when we match up the things from the first set, A, and pair them up with things in set B, the first set has to come first. A, B, or C should be in the x-coordinate, or the first thing in each ordered pair. The second thing should come from set B. So this, it is not a function from A on to B. If they asked us, is it a function from B on to A, then it would qualify. Because, you know, that would mean B is our domain set. That would be the first thing in each ordered pair, a number. And that's what we have here. 0, 1, 2, 3, they're all different. So this is a function from B on to A, but not A on to B, and that's what they were asking us. So that's a little twist on that one. Always got to be careful. Okay, this one here, determine if the equation represents y as a function of x. That just means as a function of x. X is our independent variable, so we want to solve for the other one. So to solve this for y, we would just add 4x squared to each side. So we have 4x squared plus 36. Y equals a single thing. You know, we didn't have to square root both sides and get positive and negative roots. So yes, that is a function. Number 38. Evaluate the function at the specified value and simplify. Ooh, and here it says and simplify. That's a little different from the ones we did. So here is our g of y function. That is 7 minus 3 times y. So letter A. G of 0 is equal to 7 minus 3 times 0. And 7 minus 3 times 0 is 7 minus 0, or just 7. Letter B. Now we're plugging in 7/3. Ooh, it's a fraction. Everybody hates fractions. G of 7/3 is 7 minus, and this 3 times y, or whatever our input is. We're going to have 3 times 7 over 3. And this might be easier if I put a 1 under that initial 3. So we make this 3 over 1 times y, or 3 over 1 times 7 over 3. So here we're going to have 7 minus. On the diagonal, the 3's cancel or reduce to a 1, so we're left with 7 over 1, or just 7. 7 minus 7 is 0. Last but not least, G of s plus 2. So we have our 7, that's just a number, minus 3, and we're replacing the y, or this variable, with the quantity s plus 2. And they did tell us to simplify, so let's distribute the negative 3. 7 minus 3s minus 6. And now we can combine the 7 and the minus 6 into a 1 minus 3s. Alrighty, we're almost home. Last one is the piecewise defined function. So first is f of negative 2. We got to figure out what piece of the piecewise function that goes into. Negative 2. Our number where we switch around here is 1. So if we're less than or equal to 1, which negative 2 is, we use the top piece. X squared plus 2, or negative 2 squared plus 2, which is 4 plus 2, or 6. Letter B, f of 1. So if we're less than or equal to 1, that's the key right there. That number 1 is where we're switching from one piece to the other, so we got to look for the or equal to sign. We're plugging that 1 into the top piece of the function. So 1 squared plus 2 is 1 plus 2, or 3. And last is f of 2. If we're less than or equal to 1, we use the top piece. Now we are greater than 1. So we're using the bottom piece, 2x squared plus 2. So 2 times something squared plus 2, and that parentheses is filled with the 2 that we're running through that function. And now here's a good question. What do we do first? Do we square the 2 first, or do we multiply the 2 times 2 and then square that result? Remember order of operations, grouping symbols, parentheses first, and then next would be exponents. So we definitely want to do the 2 squared. This 2 squared turns into a 4. 2 times 4 is 8 plus 2, and 8 plus 2 is 10. And that is going to wrap up the first video for this section 2.2. Here's the assignment for tonight if you forgot your assignment paper. Numbers 1 through 4. All of those, 5 to 21 odd, and then these select problems. Remember, check the odd answers in the back. You can check the answer to these odd ones in the back of the book. And the odd ones, a lot of time, are paired up with even ones right next to them. That 33 is right next to 32 and 34. These are kind of close to 30. Check the odd ones in the back. If you got them right, you know what you're doing. And it's more likely you'll get the even ones right. When I check your homework, I'm looking mostly at the even ones. And I'll see you in the next video.